Good day, everyone. Welcome to lecture number 33 of this lecture series on computer organization and architecture. In this particular lecture, we are going to discuss how we can implement virtual memory using page tables. So in our previous lecture, in lecture number 32, we discussed what is a virtual memory and how we can implement it. So we have discussed one technique. So one technique was that for every byte or word in virtual memory, we will allocate one byte or one word in main memory. And the mapping will be stored in a table which is called a mapping table. However, this technique was having some limitations. One was that the size of mapping table was large, was significant. The second was that it loses spatial locality. Okay. Then we said that instead of having this technique, let's have a different methodology. And that methodology was page tables, implementing virtual memory using page tables. And this particular lecture is about this particular scheme. Okay. So what we are doing in that particular technique. So let's suppose we have a process. Let's suppose process 1, we have process 2. This process has been created and our operating system or our processor assumes that this process takes 4 GB of virtual memory and this process also has 4 GB of virtual memory. Okay. Or we can say this process requires 4 GB and this process also has extensive 4 GB. What we are doing, we are dividing these virtual memory into fixed size blocks. And this fixed size block is called a page. Okay, fine. So also we are dividing our physical memory. Physical memory in these fixed size blocks, the same size blocks, and these blocks are called frames. So physical memory blocks are called frames and virtual memory blocks are called pages. Okay, so now what happens? So this is our physical memory. Let's say this is my physical memory. Fine. And I have divided this physical memory in frames, fixed size frames. So let's suppose this is frame 0, this is frame 1, this is frame 2, this is frame 3, and so on. So let's say we have two processes, process 1 and process 2. Okay, we can have multiple processes, but I am only giving the example of two processes here. Fine. So now what happens? So this P1 requires 4 GB of virtual memory and this also has 4 GB of virtual memory. We divide its entire 4 GB. So basically this is stored in secondary storage. We divide this 4 GB into pages. Okay, so P1 has its pages and these pages are stored in the secondary storage. Likewise, P2 also have its pages. Now let's say my processor is running these processes P1 and P2. What it does, from these pages, it will bring some of the pages from this memory to this memory, to the physical memory. Because whenever we have to run a program, we want that the page should be loaded from the secondary storage into the primary memory. And our program should be there in the primary memory. Okay. So let's say I got some pages, page 0 and page 1. And these are pages of process 1. Okay. So let me write it here, process 1, page 0 of process 1, page 1 of process 1. Likewise, let's say I want to get page 5 of process 2 and page 6 of process 2 into the memory. So I will map this page to one frame, this page to another frame, this page to another frame, and this page to another frame. Okay. So I have loaded pages into the frames. So this one contains P0 of process 1. This one contains P1 of process 1. This one contains P5 of process 2. And this one contains P6 of process 2. So what we are doing, we are loading pages into frames. But my computer system should know which frame contains which page. So for example, this frame contains page 0 of process 1. This frame contains page 1 of process 1. This frame contains page 5 of process 2, and this frame contains page 6 of process 2. So how will we store that particular information, this map? So what we are going to do, that for every process, we will have a page table. Okay. Before discussing this page table, let's go back here. So, or let me write it here. So let's say I have virtual memory of 4 GB and physical memory is of, this is virtual memory, physical memory is of 2 GB. So how many pages will be there in this particular system? So for every process, how many pages will be there? So let's say each page is of size 4 KB. So number of pages will be 4 GB divided by 4 KB. Okay, this is equal to 4 into 2 raised power 30 divided by 4 into 2 raised power 10. It is 2 raised power 20. Fine. So 2 raised power 20 pages are there. And how many frames will be there? The frames will be 2 into 10, 2 raised power 30 divided by 2 into 2 raised power 10. Fine. So it is, so 2 into, so it is 4 KB, 4 into 2 raised power 20, it is 2 raised power 19. So there are 2 raised power 19 frames, and this frames is physical memory. And these pages for every process. Every process. Okay. So what we are going to do, the virtual address, the processor generates the virtual address. And let's say virtual address is of 32 bits. So it is a 32-bit address. And in this particular machine, physical address will be how many bits? 31 bits. Why only 31 bits? Because it is only 2 GB memory. 2 GB will be 2 raised power 31 bytes. Okay, 31 bits. So what we are going to do, as we know that every page is of size 4 KB. So we will divide this virtual address into 2 parts. This part will be an offset and this part will be a page number. So this offset determines byte inside a page. Okay, and this determines the page number. So here you can see that we have a 4 KB page. So that means 4 KB will be 2 raised power 12 bytes. So that means we will require 12 bits as offset. So 12 bits will be offset and 20 bits will be page number. So that means using this virtual address, we can have 2 raised power 20 pages. So as I said here, that 2 raised power 20 pages are possible for every process. Now, when we have a virtual address, okay, but what we want to do, so in our scheme, we have, this is our physical memory, and these are the frames. So every frame has a frame address. Frame address. Okay. And as I said, that in these frames contain pages. Pages of different processes. The question is, the first question that you have to understand is, can two processes have the same virtual address? So the first question is, can two processes have same virtual address? The second is, can two processes have same physical address? This one is possible and this one is not possible, because virtual address, every process has its own virtual address space and it can collide with others, but physical addresses are unique to every process. Fine. Now my processor is there. The processor generates a virtual address, and we know that this virtual address is the address of some byte inside some page. Okay. So what we are going to do, we will divide this virtual address into two parts. The first part will determine the page, which page, and second part will determine the offset, which byte inside the page. Okay. Then after that, from this we have to convert this page into frame. Frame means in which frame this page is located, whether it is located in frame 0, frame 1, frame 2, or some other frame. Okay. And then after finding the frame, let's say we found out that this page is mapped here, it is available here. Okay. Then what we are going to do, after finding this page here, we will then use these bits, offset bits, to determine the byte inside this page. Okay. So this offset will then determine byte inside a page. So what we have to do, we have to translate page number into frame number. Or we can say we have to translate a virtual address into physical address. And how we can translate it? We can translate it using page tables. So what is a page table? Page table is basically a table that stores a mapping of a page to a frame. Mapping of a page to a frame. Okay. Okay. So for every For every process, there is a page table. Okay. What I mean to say, for example, this page table, this process has, let's suppose, 2 raised power 20 pages. So for this process, we will have a table, this page table. Okay. And this page table, it will be indexed by the page number. Okay, so it will be indexed by a page number. Okay, so it is indexed by the page number. So when my processor generates a virtual address, okay, so from this virtual address we will get the page number, and using that page number we will access this table. Let's suppose it points here. So this location stores, this every location stores the frame in which the corresponding page lies. Okay, fine. And so that means every entry here in the page table stores the frame number. Okay, so let's suppose our frame number is of 19 bits. Then every entry will store 19 bits. And we know that every process has its own page table. So whenever processor generates the page ID of a, whenever processor generates the virtual address for any process, so we have to access the page table of that particular process. Okay, so let me explain it in detail. So now what we are going to do, so we have our processes P1 and P2, and their pages have been created. So likewise, P2's pages are also created. Now we have our physical memory. So this is our physical memory. This physical memory has been divided into frames. Let's suppose this is frame 0, this is frame 1, this is frame 2, this is frame 3, and so on. Now, let's say we have populated the physical memory with some frames. Let's suppose frame 5 of process 1, frame 7 of process 1, frame 3 of process 2, page 0 of process 2, page 6 of process 3, page 7 of process 3, and so on. Now let's say this is my, and this mapping will be stored in the page table. So let's say we have 3 pages. So we will have 3 page tables. So this is our page table 1 for process 1. And likewise, we will have page table 2 for process 2 and page table 3 for process 3. So let's say these are the entries. Fine. Okay, so let's say this is my processor. So processor generates, let's say currently we have process 1 which is getting executed, and process 1 has generated a virtual address. So what we have to do, we will divide this virtual address into 2 parts. So one will be the page number and another will be the offset. So then we will have a translation unit. Okay. What this translation unit is going to do, it will see this translation unit, which is the process ID, and what is the page number. Then it will access the page table of this process ID. Okay, so let's suppose it is process 1. So it will access this page table. So let's say page number is this page number P51. Okay, so it will go here. Let's suppose it is here, page 5 of 1. So here we will have stored that it is stored in frame number. So this will give us frame number. Now translation will give a new address. The new address will contain frame number plus offset. And this frame number it will get from the process table. Now this will be our physical address. This physical address will be sent to our memory system, and memory system responds with the corresponding word or corresponding byte. Okay, so this is how virtual address is implementing using a page table. Fine. So this kind of page table that we were discussing, it is called a single level page table. So let me give an example. So for example, let's say for every process virtual memory is 4 GB. That means virtual address is 32 bits. Likewise, let's say physical memory is also 4 GB. So that means physical address is also 32 bits. Fine. And let's say the page size is 4 KB. So how many pages will be there for every process? It will be 2 raised power 20, and number of frames will also be 2 raised power 20. Okay. So let's say in this process we have in this processor we have one process. So for this one process we have to create one page table. And this page table, how many entries will be there in this page table? So it depends upon the number of pages, because for every page there will be a entry in the page table. So this will be our page table. And how many entries will be there for every process? 2 raised power 20. So this is the page table for process 1. So it will have total 2 raised power 20 entries. And every entry stores how many bits? 20 bits. So what will be the size of one page table? It is 2 raised power 20 into 2 raised power 20 bits. Okay. Fine. I can write 20 divided by 8 into 2 raised power 20 bytes. So that is 20 divided by 8. It is 1.5 megabytes. So it is for one process. Let's suppose I have 20 processes, or let's say 100 processes. So having 100 processes, what is the memory required to store the page table for all the processes or the 100 processes? It will be 100 into 1.5 megabytes. That will be 150 MB. Okay. So let's say my physical memory is 500 MB. So out of 500 MB, 150 MB is used to store page tables. And that is more than this 150 MB is nearly 30% of the main memory. So that means having this single level page table, so nearly in this particular scenario, nearly 30% of memory is used to contain page tables. And this is very significant amount of memory. So we need a methodology to have lesser size of page tables in order to save our memory. Okay. And what is the intuition? How we can decrease the size of page tables? Let's discuss it here. So let's say, for example, for every process, so we will see what is the intuition, by which intuition we can decrease the size of page tables. So let's say we have a process, okay, and we know whenever a process is created, a virtual memory of 4 GB is there for this particular process. So why I am saying 4 GB? I am assuming that I have a 32-bit system. So in a 32-bit system, we can have 4 GB virtual memory. So this 4 GB virtual memory will be like this for a process. It will have a header, and then after that, we will have a text section. Then after that, we will have data section. Then we will have BSS section. Then we will have heap section. Then we have this free memory. Then we have stack on the top. So this in between memory is free. So it is used only when stack grows or heap grows. Okay. This particular memory for most of the processes is of no use. It is there in the virtual memory, but actually it is not getting used. Only this portion is getting used and this portion is getting used. So for every process, this makes nearly maximum, even for the largest processes, this is nearly 3 MB. So out of 4 GB of virtual memory, only 3 MB is used. Okay. So 3 MB, if we convert it into the pages of 4 KB pages, so it will be how many pages? So 3 MB, so 3 MB will be 2 raised power 20 divided by 4 into 2 raised power 10. Okay. So it will be 3 divided by 4 into 2 raised power 10. So approximately it is 2 raised power 10 pages. So that means we are using only effectively 2 raised power 10 pages. Okay. So, but here, how much pages we are allocating? We are allocating 2 raised power 20 pages. Okay. So, but out of these 2 raised power 20 pages, only 2 raised power 10 pages are getting used. So instead of having a page table that stores the entries for all 2 raised power 20 pages, let's only store entries for only 2 raised power 10 pages. Okay, so that the size of page table decreases. Fine. This is the intuition behind decreasing the size of page tables. And how we can achieve that? That is achieved using 2-level page tables. Okay, so let me discuss it here. So it is 2-level page table. So the first simple approach was single level page table, but that approach has the disadvantage that the size of page tables is very large. In this second approach, we want to decrease the size of page tables. Okay. So in this particular approach, what we are doing? So for every process, let's suppose every process has 2 raised power 20 pages. Okay. So that for every process, we have a virtual address, and in this virtual address, this page number is of 20 bits and frame number is, and this is the offset. Okay. So let's only discuss about this part, because this part is used to index page table. Now what we are doing? In this part, we divide this part into 2 parts. So this 20. So let's say I am dividing it into 2 parts, 10 and 10. Okay. This 10 and 10. These most significant bits, these are used to access a page table. Okay, this will be called a primary page table. So that means what will be the size of primary page table? So let's suppose this is primary page table. And how many bits we are using to index this primary page table? These 10 bits. So there will be 2 raised power 10 entries. And now this entry in the primary page table, this is used to store address of another page table. And that another page table will be the secondary page table. Okay. Now, how many? So this is for every process. So how many primary page tables are for every process? One primary page table. And how many secondary page tables are possible? 2 raised power 10. Not 2, yes, 2 raised power 10 secondary page tables. Okay, because this one points to some other, this points to some other, this points to some other page table. Now let's see how we are decreasing the size. So this is our primary page table. And these are our secondary page tables. 1, 2, whatsoever, how many secondary page tables are there. And we can access these secondary page tables from the primary page table. Let's say processor generates a virtual address, and virtual address, from that virtual address we will get the 20 bits, that is the page address. From these 20 bits we will separate it into 10 and 10. This 10 is used to index primary page table. So from the primary page table we will get the address of secondary page table. So let's suppose it is saying go to this page table, this one, secondary page table. Okay, now after choosing the secondary page table, these 10 bits are used to access the secondary page table. And from, let's suppose it points here in the secondary page table, this will contain the frame number. So that means what is going to happen? So when my processor, so let me write it in algorithmic form. So processor is there. It sends a virtual address. This virtual address goes to address translation system, and this address translation system gives the physical address. Okay, so virtual address has 2 parts. This is page number and this is offset. And physical address has 2 parts, frame number and offset. So what is translation unit doing? From this virtual address, it will take the page number, this address translation unit. This is page number. And it will divide this page number into 2 parts. This part will access primary page table, and this part is used to access secondary page table. Okay. So now from this, we will first access primary page table. So this is our primary page table. So let's suppose it points here, and this gives us the secondary page table. Because there are n number of secondary page tables, so it will give us one secondary page table. Let's suppose it is saying choose this secondary page table, this one. So after choosing this secondary page table, we will use these bits to access this secondary page table. Let's suppose it points here. So from this location, it stores the frame number. and this frame number will be put here to give the physical address. Now, where is the storage? How we are saving the storage? Let me show you here. So we are saving the storage by not storing all the secondary page tables. Okay, what does that mean? We will use only those secondary page tables which may contain actual pages, because there are multiple pages, n number of pages that are not used by the processor. So we won't store those page tables. And if we are not storing the page tables for those pages, that means we are storing the memory. Okay, so let's say our page table, primary page table will contain 2 raised power 10 location, 2 raised power 10 locations. This is the primary page table. Okay, now this primary page table, as we know that every location points to a secondary page table. And there are total 2 raised power 10 secondary page tables possible. So that means every location can have to store 10 bits. So what is the size of primary page table? So size of primary page table will be 2 raised power 10 into 10 bits. Okay, and this will be equal to 10 kilobits or 1.25 kilobytes. Now let's suppose we are storing an secondary pages for every process. Okay, and for every secondary page, size of one secondary page will be equal to 2 raised power 10, because every secondary page is also pointed by 10 bits, is also indexed by 10 bits. So it will be 2 raised power 10 into frame number. Let's suppose frame is of 20 bits. Frame number is of 20 bits. So it will be 20 kilobits or 2.5 kilobytes. So let's say we have to store n secondary pages. So the size of total page tables for one process will be is equal to size of primary. What is the size of primary? 1.25 KB plus n into 2.5 KB. This will be the size of single page table for one process, or the size of all the pages for one process in two-level page table. So you can see that this helps us to decrease the size of page tables. Okay, so let me summarize the one-level page table or single-level page table and two-level page table. So in a single level page table, we have one page per process or one page table per process. Okay, and this page table is indexed by page number. In two-level page table, we have one primary page table plus n secondary page tables for every process. And in two-level page table, page number has two parts. is divided into parts. One part is used to index primary page table and second part is used to index secondary page table. So this primary page table, every entry of the primary page table stores the address of secondary page table, and every entry of secondary page table. So this is primary page table. So by using the data stored in primary page table, we can choose one of the n secondary page tables. Okay, and then after choosing the secondary page table, the remaining bits of the page number, this part, is used to access that particular secondary page table, and that secondary page table stores the frame numbers. This is how two-level page table works, and how it is able to decrease the total size. It is able to decrease the total size because we are not storing all the secondary pages. We are only storing, or we are only creating those secondary page tables which are required by our process. Okay, so this is one-level page table and two-level page table. Now there is another improvement, that is inverted page table. Okay, let's see what is an inverted page table. So in some of the processes, what they are doing, so actually what we were having a page number. So in our actual case, so this was our page table, and this page table was indexed by page number, and we get the frame number. Now inverted page table, what it does, it says that let's have a single page table for entire processor. So here we were saying one page table for every process, but here we want to have a single page table for entire processor. This page table will be indexed by a frame number. Let's suppose how many frames are there? 2 raised power 20 frames. So that means frame number will be how many bits? 20 bits. So this will be our page table, inverted page table, and this will be indexed by frame number. And every entry stores the page number plus process ID. Okay, what I mean to say, for example, let's suppose this is my inverted page table. Inverted page table. So this inverted page table gets a frame number. Okay. And from the frame number, let's suppose it points here, it will give us the page number plus process ID. Okay. So this is hypothetical concept. Actually, how it is implemented, I will show you that. But here it is hypothetical. Why? It is hypothetical because our processor generates virtual address, and virtual address has page number plus offset. But we are accessing this page table, inverted page table, using a frame number. Where will we get the frame number? Okay, we have no method of getting the frame number. So how we can implement this particular methodology? Let me show you how this is actually implemented in the processors. Okay, so what is happening in the process? So when my processor generates a virtual address, okay, this virtual address, from this virtual address we will get the page number. We will combine this page number with the process ID. Okay, then we will get the hash value of this, hash of page number and process ID. This hash value is used to index a table. Okay, so it will be like this. We have a table. Okay, this is our hash table. So we are getting page number plus PID. We will get it as hash, and using that hash we will check the hash table. Let's suppose it is pointing here, so this will point to one entry in this particular table, and this table or the entry of this particular table will contain page number plus process ID. Now, see, we are giving the input as page number and PID, and output is also page number and PID. So it doesn't make any sense. Actually, what we are getting after we get this page number and PID, and input was also page number and PID, we will compare these two. If this one and this one is same, then we will get the address, this address. Okay, and this address will be our frame number. Then this frame number will be used as the output. Okay, let me explain in detail again. So let's discuss it again. Okay, so let me summarize this. So this is our processor. Processor sends virtual address. So this is the virtual address. In this virtual address, we are taking the page number. Basically, our aim is that from virtual address, we should generate physical address. Okay, the physical address has offset and frame number. So this page number plus process ID. Okay, so we calculate the hash. So we can use any hash function. Then this hash value is used to index a table. So this is a table. So this table contains some value. So let's suppose this value. Okay. Using this value, we index another table, which is the inverted page table. And this inverted page table stores the page number plus process ID. So that means from this page table, we will get page number plus process ID. We will compare this one with this one. So if they are same, there are two choices, they are same. Same means that this value points to this particular page number. So this particular value will be the frame number. Okay. And when this can be different, this can be different because there is a possibility that multiple values have the same hash. Okay. So there is a possibility of collision. You may have already studied about the collisions in hashes. So multiple page number plus process IDs may have same hash value. So they will point to the same location. But we will consider this value as valid only if this is same page number and process ID which is used to index this particular inverted page table. Okay. However, if this does not match, then we will assume that there is a miss. Miss means that this particular page is not available in the physical memory. Then we have to get that particular page into the physical memory, and we have to update this particular inverted page table as well. Okay, this is the mechanism for inverted page tables. However, you have to remember that this is not most widely used, this particular scheme. Only single level and multi-level page tables, or we can say two-level page tables, are used. These are very rarely used, these inverted page tables. Right? So with this, we have completed 3 techniques of implementing virtual memory. One is using single level page table, the next was using 2-level page table, and the third was using inverted page tables. Okay, so we completed these 3 parts. Now our query is how to fill these page tables, or let's only consider 2-level page table or single level page table. Okay, how we will fill these page tables. Okay, and after filling page tables, what are the issues that we have to solve? Let's now discuss those things here. So see what we have discussed up till now, that how to handle multiple processes using virtual memory. Then we discussed how to actually implement virtual memory technique using page tables. However, we have not discussed anything about the size problem. Size problem. What is the size problem? Size problem means that if I have a process or I have a program that actually needs, let's suppose, 3 GB of physical memory. We have already allocated it 4 GB of virtual memory, but we are saying that 4 GB of virtual memory we have allocated to this program, but in reality it requires 3 GB of primary memory, and let's say we have only 2 GB of primary memory. Then how will we handle it? What we are going to do, we know that we have a program of 4 GB, virtual memory 4 GB. So we are converting this 4 GB into pages. These are virtual, we know virtual pages. And in these 4 GB pages, 3 GB are those pages which are actually used. Actually used. Okay, or in other words, I can say, let's suppose I have process 1, process 2, process 3. Process 1 needs 1 GB of actual memory, process 2 needs 1 GB of actual memory, and process 3 needs 1 GB of actual memory. So total we need 3 GB of memory, but there is only 2 GB of memory, physical memory. Okay, so in our physical memory, this is our physical memory, we have frames. And these frames can hold only 2 GB of memories, 2 GB content, okay? But we need actually 3 GB content in this portion. So that means some frames of these processes are to be stored somewhere else. Okay, and this somewhere else, storing the frames of processes somewhere else, this is usually chosen as some part from secondary storage. So what is there? So we have main memory. So this is our primary memory, and it contains frames, multiple frames. Okay. And this is our secondary memory. And from this secondary memory, some part is chosen. And this part is used to hold frames or extra frames, which cannot be placed in the main memory. So those frames will be placed here, and this place is called swap space. Now we have a page table. So this is our page table, single level page table, and we know it is indexed by a page number. Now there is a possibility that this particular frame is not available in the primary memory. So it is available in the swap space. Okay, because there was no space available in the primary memory, so we placed this particular frame into the swap space. So my system should know whether this frame is in the primary memory or in the swap space. Okay, and how will it know? We will add an extra bit here. So this is the extra bit, and this extra bit will tell us whether this frame is present in the primary memory or it is present in the secondary memory. Okay, so if this bit is 1, so that means the frame is in main memory, or if it is 0, it means it is in swap space. Okay, and whenever, let's suppose I want to get a page, some page, so that means it points to some frame. Now if I get this frame is in the primary memory, so I will get data from the primary memory. However, if this frame is not in the primary memory, it is in the swap space, then what I have to do, I have to get that frame from the swap space and place that into the primary memory. Then I can use that particular place. So you can see that there we have this primary memory, we have the swap space, and pages are interchanged in between these two, not page frames, between these two memories. So let's say it is 2 GB primary memory and we have selected this as 3 GB. So effectively we can say we have 2 GB plus 3 GB of primary memory. But actually our primary memory is only 2 GB, but we can extend it to 3 GB, this 5 GB. Okay, so using the swap space, we can even hold programmers that have size larger than the primary memory. So this is the use of swap space. Okay. Now comes another concern. The concern is, so now let's discuss another thing here. So let me wrap this portion. The concern is, for example, my process or my processor is sending a virtual address. Okay, so my processor, it sends a virtual address. Virtual address means that it has to access memory. Okay, so this virtual address goes to address translation unit. This address translation unit will access the page table. And we know this page table is stored in main memory. After accessing the page table, we will get the frame number. Then getting this frame number, we will have the physical address. This physical address is then sent to the memory, and we will have another main memory access. So you can see that in this particular scenario, whenever we have to access a memory, so to access a memory, we have to access it how many times? 2 times. One for accessing the page table and another for accessing the actual data. So for every memory access, we have to access the main memory 2 times, because once we have to access it, we have to access it for the page table, and that will decrease our performance. We want that this particular scenario, this should be minimized. Minimized means we should not access the main memory for accessing the page table, but we have to access the page table. There is no way that we can get the frame number without accessing the page table. So how can we minimize this? We can minimize this by caches. Okay, what does that mean? How we can minimize it by caches? So let me write it here. So what we are going to do, whenever we have a process is running, okay, in the processor itself, we have a separate cache. That is a small cache, very small cache. This particular cache, in this particular cache, we will store some part of page table. So in reality, page table was stored in main memory. So some part of this page table is stored in this cache. So which part? We want to store that part which is getting accessed most of the time. Okay. Now, when my processor is sending a virtual address, okay, so from this virtual address, we need to get the physical address. So to get a physical address, we have to access what? Page table, and page table is in main memory, but some part of page table is in this particular cache, separate cache that contains the page table. So instead of accessing the memory, we will access this particular cache, and we will check whether that part of the page table is present in this cache or not. If it is present in this cache, then we can easily get the physical address from that particular portion. However, if that particular entry is not present in this cache, then in that scenario, we have to access the main memory. Okay, so this cache that is used to store some part of the page table is called Translation Lookaside Buffer. Okay, so what is the complete scenario? The complete scenario is like this. So let me write in detail. So we have a processor. The processor sends a virtual address. Okay, and we will access the translation lookaside buffer, TLB. So if there is a hit in the TLB or miss in the TLB, so hit means that I am able to find that portion of page table in the TLB which contains this virtual address. So if there is a hit, that means in the TLB itself, I can get the physical address. Okay. However, if there is a miss, then I have to access main memory. Access main memory page table. And then we will get the physical address. So this part takes only fraction of a second. and this part takes nearly 100 cycles. Okay, so we want that the TLB should have maximum hit rate, and in most of the scenarios hit rate is more than 90%. Okay, so TLB plays an important role, and it is one of the important structure that maximizes the performance of our system. Okay, and when we are checking the TLB, when in the execute stage of the pipeline, when we are getting the virtual address, we in the execute stage itself, we send this virtual address to the TLB, and after completing the execute stage, if there is a hit in the TLB, we will get the physical address. Then this physical address will be used in the memory access stage. However, if there is a miss, then after the execute stage, we have to wait nearly hundreds of cycles to get the physical address. Then we can start the memory access stage. Okay, so this TLB plays an important role, and we have to design this TLB in such a way that we should get the maximum hit rate in this particular scenario. Okay, so this completes our various parts. The first part we completed was the implementation of virtual memory using page tables. And in the page tables, we discussed various page tables: single level page table, two level page table, and inverted page table. Then we discussed the need of swap space. And here we discussed the need of TLB and how important it is. Now we have one last part that we have to complete, that is memory management unit. And in this memory management unit, we will discuss how page tables are handled. So let's discuss this portion now, and that will complete this particular lecture. So let's see how page tables are managed. So for that, we have to discuss about the memory management unit, MMU. Memory management. This particular unit is responsible for translation of virtual address to physical address. And so first is virtual address to physical address. Second, it is responsible for handling page tables. Okay. And this MMU, it can be either a hardware, a separate hardware. So there is a separate logic for MMU, or it can be a software process. But mostly it is the hardware that is used as a memory management unit. So let's see what happens, how it handles all the issues. So when a process is created, so we have a process. So it has been created. So it has been created, it means that its pages are created. And necessary updates are done in the TLB. What are the necessary updates? That means if some process was already running, then the entries related to that particular process, to the previous process in the TLB, are free. Okay, now we have to put a new data in the TLB. Fine. So whenever in explaining this MMU, we will consider that every process has a two-level paging technique, two-level pages. So it has primary page and secondary page. Sorry, primary page table and secondary page tables. Right. So what it does, so what our MMU does, whenever a process is created, it creates a primary page table into main memory for that particular process, and also creates necessary secondary page tables. not all page tables, but only required secondary page tables. Okay. Then whenever my processor sends a virtual address, okay, this virtual address goes to memory management unit. What this memory management does, it first finds the primary page table of this particular process. And how it will find this particular primary page table? Basically, this primary page table is stored in primary memory. So it requires the starting address of primary page table. Okay. And this should be the actual physical address, not some virtual address. Physical address of page table, primary page table. And this starting address is usually stored in a special register or at some fixed location. So after getting this starting address of primary page table, this MMU uses the virtual address to access this primary page table. Then from the primary page tables, it accesses the secondary page table to get the final physical address, and the output will be the physical address. Now the issue is, what will happen here is that, so let's suppose processor is sending an address for some, so let me make it clear here. So processor sends a virtual address goes to MMU. Okay, MMU checks the TLB, first TLB. Okay, and in the TLB there will be a hit or miss. So if there is a hit in TLB, we will get the physical address. However, if there is a miss, then my memory management unit has to access main memory. Then in the main memory, it will first access primary page table. Then using this primary page table, it has to access the secondary page table. Now there are also two choices. One is secondary page table for this page exists, and another is does not exist, because we have not created all the secondary pages. This will be scenario when our page, the page that we wanted to know, it does not exist or it is not there in the main memory. We have not used this particular page. So it is also called a page fault. So in this particular scenario, we have to create a secondary page table and also bring page from secondary memory and place in the primary memory. So secondary page table exists. So we have to access secondary page table to get the frame number. Now there are also two chances. One is that the page that I am asking for, or the frame that I am asking for, it is available in primary memory. Another is it is not available in primary memory, but it is available in swap space. So if it is available in primary memory, I will get the physical address. Okay. And I will access that particular frame. However, if it is in swap space, then what we have to do, we have to bring frame from swap space and place in the primary memory. Okay, and in this case, in this particular scenario, there may be a possibility that my primary memory is full. Then we have to do some replacement strategy. For example, we can use least recently used or mostly recently used. Whatever the replacement strategy we have to use, we will replace some frame from the primary memory, put that frame into the swap space, and the frame that we got from the swap space we have to put at that particular location. So this is not the complete flow, but this is how the flow happens. And we want that our system should be such that we have maximum hit rate in the TLB. So this should be one goal, maximum hit rate. Second, if there is a miss, then our processor or our design is such that this scenario is going to happen only rarely. So only 0.0001% of time this scenario should happen. This scenario means that I am not able to find the page in the primary memory. So this scenario, not finding a page in the primary memory, this is called a page fault. Page fault. So in that particular scenario, we have to get the page from the secondary memory and put into the primary memory. And this takes, sometimes it takes millions of cycles. So we want that page fault should be minimal and high hit rate in the TLB should be maximum. And this whole scenario is taken care by the memory management unit. Okay, so I am not going into the detail of memory management unit, how actually we are bringing frames from the swap space, because it is not the part of this particular lecture. It is out of scope of this particular lecture. And for greater details, greater understanding, and understanding the details of this memory management unit, you can take the operating system course where it is to be discussed in great detail. So here we are only discussing it briefly so that we get the higher level view how processor is handling all these things. Okay, so with this we completed the discussion about the virtual memories. So our previous lecture, that is lecture number 32 and lecture number 33, they were about the virtual memory and how we implemented virtual memory in using the page tables. So let me summarize what we did. First thing was that we have two problems. The problems were first overlap problem, and the second was size problem. Okay, and we handled both these problems using the concept of virtual memory. But then comes the question how to implement virtual memory, and this can be implemented using page tables. And for page tables also we have three different strategies. One is simple page table or single level page table. One is two level page table and another is inverted page table. But this is rarely used. These two are mostly used. Then after the page tables, we discussed the requirement of swap space and TLB, Translation Lookaside Buffer. After that, we discussed how we do the translation from virtual memory, from virtual address to physical address using the memory management unit. So this does the translation as well as management of page tables. Okay, and at the end we reached that we want two things in our entire system in order to improve the performance. First, maximize TLB hit rate, and second is minimize page faults. Okay, so with this we will stop this particular lecture here and we will meet in the next lecture with a new topic. Till then, goodbye.